Hello Year 10, it's Miss Bailey here. Please have the worksheet that's attached on the Padlet to hand so that you can be filling in during this video. For your do now, there are 3 retrieval questions for you to have a go at. Please pause the video whilst you have a go at these. There is space on your worksheet to write your answer. So for the first question, the answer should have been zinc chloride. So the first part of the name coming from the metal and the second part coming from the type of acid. But as you can see in the picture, we also have another product which we can see by the effervescence that has been produced. And this is hydrogen gas that has been produced as well as this zinc chloride salt. So the next question is, how can we test for this gaseous product? And that's referring to the hydrogen gas. And the answer for this is using a lit splint. And if there is a squeaky pop, then we know that hydrogen gas is present. And the reason for this squeaky pop is due to the high energy that's released when the hydrogen gas is ignited and it reacts with oxygen. So because of that high energy release, that's what causes that squeaky pop, which would produce more effervescence on a reaction with hydrochloric acid, calcium or magnesium. So the answer to this is calcium, and that is because calcium is lower in group 2 than magnesium, and that means that it can lose its outer electrons easier than magnesium, because they are further from the positive nucleus and therefore there is a weaker attraction holding those outer electrons and therefore they get lost easier. So today we're going to be looking at salts, both the formula and the structure. So this is going to be recapping a bit of last lesson and also a bit of our previous topic looking at structure and bonding. So just a reminder of the acid and metal reaction. So we just looked at that example where we had zinc reacting with hydrochloric acid to produce zinc chloride and hydrogen gas. But we deal with different acids to just hydrochloric acid, and that determines what X is going to be in each case. So we might already be familiar with the idea that hydrochloric acid is HCl, so that chloride is the counterpart to the hydrogen in the acid, and so therefore that chloride ion carries through into the salt component. So can you have a go at completing the table here? So I've put a hint here that the ion charge is +1 for hydrogen. So can you work out what the X component is for each of these acids and also what the charge is? Pause the video whilst you have a go at this. So this is the answer for the first column. So as you can see, we've got our chloride that we were familiar with from before. We've got sulfate and we've got nitrate. So the parts that were not hydrogen belonged to the X. So sometimes we get ions that are made up of more than one atom, such as the sulfate and nitrate ions. With our charges, if hydrogen is a +1, then to make it neutral overall, so an overall charge of 0, then we need our chloride to be -1. With our hydrochloric acid, with our sulfuric acid, we've got 2 hydrogen ions there. So that gives us a +2 charge, and therefore our sulfate, in order to make it equal to 0 overall, is going to need to be worth -2. With our nitric acid, we've got that +1 charge of our hydrogen, and in order to make it neutral overall, so overall charge of 0, we're going to have to make our nitrate a -1. So that is the complete table there for you. If you can correct anything that you didn't get or you weren't sure on. So this is another bit of a recap. So our hydrochloric acid forms chloride salts, sulfuric acid forms sulfate salts, and nitric acid forms nitrate salts. So we just looked at the formula for those components, so chloride sulfate and nitrate. And now you can see those being used in the formulas of salts. So what I'd like you to do is to complete this table. I'll work through the first row with you as a worked example so that you then know what to do for the remaining rows. So our name of salts we always name from our positive metal ion first, so sodium, and then our Cl, that is our chloride. So in order to get a sodium salt, we must have used sodium as our metal. And in order to get a chloride salt, we must have used hydrochloric acid. So pause the video whilst you complete the remainder of the table. The composition of MX can change depending on the different charges of our metal and our non-metal ions. So we're going to have a look at this calcium chloride example. So calcium is in group 2 and therefore it has 2 electrons in its outer shell, and these both get lost when we form the calcium ion to form Ca2+. Because we've lost 2 negative electrons, we then have that overall charge of calcium 2+. With our chlorine, in order to form chloride ion, chlorine is in group 7 and therefore it only needs to gain 1 electron to form a full outer shell where it's more stable. So it gains 1 negative charge and therefore has a -1 charge overall. So for our calcium chloride, we need it to be neutral overall, and so we need there to be an overall charge of 0. So we need to work out how many of each the calcium and the chloride ions we need in order to make it neutral overall. Now there are 2 ways that you could do this. So the first way is you could use a visual diagram to compare our positive. So here we've got our calcium ion that's worth 2+, and then we have our chloride ion that's worth 1-. So at the moment you can see there are 2 positives and 1 negative. So overall at the moment we've got an overall charge of +1, but we need it to be neutral, which is overall 0. And so hopefully what you can see is that we're going to need another negative charge in order to make our number of positive charges and our number of negative charges neutral overall. So now we have 2+ and 2-, which add together to make 0 and is therefore neutral. The other way you can do it is the crossover method. So you look at the number of each charge, so where there's no number that indicates a 1, and you cross them over, so you then get Ca1, so we don't write it, and then Cl2. Be careful though, because we want to make sure that these are the simplest ratios. So if it was a 2 and a 2, we wouldn't write 2 and 2, we would want it to be a 1 and a 1. So can you pause the video whilst you have a go at the 10 examples below? So the salt that's been formed, that has been made up of both metal and non-metal ions. So when we deal with metal and non-metal ions, we have ionic bonding. And that's what we looked at a couple of topics ago, where electrons are transferred, so our metal loses and our non-metal gains. So sodium chloride is actually the salt we use for our food, so table salt, and this is what its structure looks like. So this is what we call a giant lattice, and what you can see here is that there is an alternating arrangement between our positive sodiums and our negative chlorides. So every positive sodium is surrounded by negative chlorides, and every negative chloride is surrounded by positive sodiums, and that extends throughout this entire structure. So we can think about what we know about table salts to help us with our recapping of our properties of our salts. So salts being MX in general, so not just NaCl, but all those salts that we've just looked at naming, because they all have very similar properties, and it's all a result of that structure. But we're aware of some of these from our experience with table salt. Melting and boiling points. So to start with, we know that salt at room temperature is a solid, and this tells us that they have high melting and boiling points. The reason for that, if we jump back to our picture, is because of these strong electrostatic attractions between the sodium and the chloride ions. They would need to be broken in order for us to melt and boil. So it's a high melting and boiling point due to strong electrostatic attractions between oppositely charged ions. Solubility, we just need to know that it can dissolve in water. And then conductivity. In order for something to be conductive, we need free charged particles. As a solid, they cannot conduct electricity because the ions are not free to move. But when they are liquid or aqueous, then they can, because those ions become free to move. Now remember that ions are charged, so our conditions are when are the ions free to move, and that's in the liquid and the aqueous phase, but not in the solid. So 2 questions for you to answer based on what we've just been discussing. Pause the video whilst you have a go at this. And then finally, can you fill in the gaps describing the structure of sodium chloride? Pause the video whilst you have a go at this. Thank you all for watching, and see you next time.